Hi everyone, this is the last video for this class. I'm recording this uh, in a pretty exhausted state. I'm pretty sure you're exhausted too, but I got my iced coffee. That'll perk me up. But also something that'll perk me up is this is kind of my favorite part of the class. It's like a big plot twist. It's like a big reveal. We're going to talk about the general linear model. And the plot twist is this: t-tests, ANOVAs, correlation, regression are all just different disguises worn by the same underlying person, the general linear model. It's been the same person the entire time. Dun, dun, dun. And I have some memes I'm going to share. Sorry. Mark LaCour's dank meme stash. This one, I'm an expert on stats. Oh yeah, name 5 analyses then. General linear model. That's on me. I set the bar too low. You get it? Because the expert, the general linear model is basically a bunch of statistical tests. So when she says name 5 analyses, he's naming at least 5, just right there. Here's another one. I don't know if you're familiar with the astronaut shooting the other astronaut after a big realization. I have no earthly idea. Get it? Earthly. I have no earthly idea what insanity created this meme format, but you see over here, you have t-test, ANOVA, correlations. We have not learned multi-level modeling or structural equation modeling, but they are also, they're not the same as the general linear model by itself. We've been learning the general linear model are like simple uses of the general linear model, but these are like MLM and SEM are like extensions of it. But they are basically all more or less the same thing. So you have this astronaut right here saying, wait, it's all regression because the general linear model is basically just regression. Wait, it's all regression? And the other astronaut says, always has been. And then I guess he shoots him. I never got the full story on what's going on in this meme, or why the astronauts are shooting each other. All good jokes. Like I said, the general linear model is basically regression. And I'm going to talk about the math behind all this stuff quite a bit in this chapter. I'm not so much concerned that you can do the calculations yourself. I just want you to understand why it is, not necessarily even why it is, but that it is that these tests are all the same. I'm going to show you how a t-test can be turned into a regression, and ANOVA can be turned into a regression. And that's because really it's not that they are turning one into the other, it's just that they've always been the same thing. You just never looked underneath the hood to see the real math going on underneath. But this is the general format of the general linear model. You've got y hat over here. That's our predicted level of the dependent variable. So if I'm making predictions about, let's say our dependent variable is test scores. I want to predict what your test score is. You give me another random person. I want to predict what their test score is. And I'm going to base my predictions off of the independent variables, which goes on the right side of the equation. So y hat, that's my prediction. The mandatory part is the intercept. That's the b sub of 0, a b with a subscript of 0. That gets added into every prediction. So if I want to predict your exam score, I might start by saying, okay, let's start by adding the average exam score, and then we'll adjust our prediction based on other information. So other information is basically placing a weight onto other variables. So let's say x1 is a variable that represents how much sleep you got the night before. So if you got 8 hours of sleep, x1 would be 8. So I'd imagine more sleep means a better test score. So I would end up saying, I predict that their test score is going to be the average plus and I'm going to add a certain amount to my prediction for each hour of sleep you got. So it's hours of sleep times how much extra score you think they're going to get on their exam. You add that to your prediction. And you keep going on and on with that. You add as many predictors, as much information, as many independent variables as you want to the exam. I mean, to your predictions, to your equation, until you get the last one, which is the last variable. Let's say this is the fifth piece of information. Let's say it's, I don't know, how many hours they spent studying, which I think would be the best predictor probably. Let's say you spent 2 hours studying and the regression coefficient is, let's say 5. So I would have my predicted score for you would be the average for the class plus such and such amount of points, depending on how much you slept, so on and so forth. And then you studied for 2 hours and the regression coefficient is 5. So I'm going to up my prediction by 10, 2 times 5. So I add all of this stuff to my prediction. That's the general format. And we're going to see how when you do statistical tests on the intercept and on these different regression coefficients, it's really the same thing as doing a t-test or an ANOVA. And I think it's important to learn this framework, not only because it helps you kind of get how everything's connected, but eventually, if you start really getting into research, especially if you're a consumer, I mean, not especially, but if you're a consumer of research, you should understand this pretty well. If you want your therapy or your services you provide to be evidence-based, you should understand the statistics that the research you're reading is based off of. You get a lot of freedom from thinking of things this way, and I'll show you why as we go forward. So let's start by recreating a t-test with a regression. So I have test scores. This wouldn't really be an exam. I was actually thinking bowling scores, but you know, the average, so you have the control group, the mean is 138.95. That's based on, I think, 40 people in the control group. This is made up data. That's the sample mean for the control group. For the experimental group, they got a higher score. They got an average of 169.14. So let's say the control group is just normal people who didn't receive any kind of treatment of any kind, and they took the exam or whatever this is, and they got these scores, 138.95 on average. And for the experimental group, we gave them some sort of super pills or some sort of injection or bitten by a radioactive goat, something, and it made them better at the test. So the sample mean is 169.14. If you do an independent samples t-test, then, oh, you know, it's probably based on 20 people per group because degrees of freedom is 38. Whoops. But anyway, if you did an independent samples t-test and you say, hey, look, these sample means ended up being different, but I want to know if they're, in a sense, reliably different. Or is this just sampling error? If I repeated this experiment, would they actually be different again? Would they be about the same? So you do a statistical test on it. You get T with degrees of freedom of 38 equals 2.22. And the probability of getting a test statistic that high or higher in absolute value is 0.033. That's less than 5%. So you reject the null hypothesis and you conclude that the control group and the experimental group in the population probably really are different. So that's the t-test. That should be pretty familiar by now. Let's look at this from a regression standpoint. You have your predicted Y. I'm predicting what score you're going to have. And instead of saying intercept, I'm going to say the mean of the control group. And the mean of the control group is 138.95, as you might recall. So my prediction, if you give me a random observation and you say they're from the control, like I'm going to add to all of my predictions, regardless of whether they're from the control group or the experimental group, I'm going to add the mean of the control group. But I'm also going to possibly add the difference between the groups. The difference between the control group and the experimental group is 30.19. The experimental group is 30.19 points above the control group. And so this is a regression coefficient for increasing or changing our predictions depending on our variables. And I've got this, what's called a dummy variable right here. X1 is a dummy variable. It's a weird name. I didn't come up with these names. A dummy variable is a way of coding categories. I want to categorize new observations for whether they came from the control group or the experimental group. This dummy variable X1 is going to be set to 0 if an observation came from the control group, and it's going to be set to 1 if an observation came from the experimental group. So if I need to make a prediction of what someone's test score is going to be and they came from the control group, I'm going to set X1 to 0. So in the regression equation, my prediction is 138.95, that's the mean for the control group, plus the difference between the groups times 0. Anything times 0 is 0. So this entire part of the equation drops out and you're left with just 138.95. That's our prediction for the control group. If you give me a new observation, you say predict what their score is going to be, and you tell me they came from the experimental group, now I'm going to say X1 equals 1. And so my prediction, Y hat, is going to be 138.95. That's the mean for the control group, plus the difference between groups, that's the regression coefficient, times 1. So this term stays in the equation and it gets added together to 169.14. And that happens to be the mean for the experimental group. So far, this might seem like just a weird way of restating the same thing, just in a weird regression framework. And you might not even see why this is better than just doing a t-test, which is fine. I'll get there with you, hopefully. You'll come along. So here we got a scatter plot, which should look pretty weird as far as scatter plots go. The x-axis goes from 0 to 1, but all the scores are either only at 0 or only at 1. There's no in between. That's because X represents what group are you in? Are you in the control group? That puts you at 0, or are you in the experimental group that puts you at 1? You can't be halfway in between the groups. You can't be 1/3 control, 2/3 experimental, one or the other. It's categorical. And when you run this through a regression equation, you say, hey, I want you to use X to predict Y. I want you to use group to predict test score. You'll get a regression line. It'll give you an intercept and a slope. And this line is going to run through the mean of the control group. The line runs right through the mean right here at the intercept, and it slopes upward to get you to the mean of the control group. So the line is going through both means of both groups. And if you work through the math with the dummy coding, you get my predicted Y hat is just the intercept, just this, when X equals 0, 0 for control group. And the math works out to my predicted score, Y hat, equals the intercept, that's right here, plus 1 times the regression coefficient, B1. That boosts our prediction from here to up here because X went from 0 to 1. Technically, you could, if you wanted to, multiply the regression coefficient B1 by 0.5, and it would give you whatever this number is right here, but that wouldn't make any sense. The math doesn't care itself, but you as a human should know that makes no sense. So side by side, we have 2 different ways of representing the same data. You have a bar chart showing this is sample mean number 1, this is sample mean number 2. Or you could have a scatter plot where you say, look, here are all the data points spread around for the control group, and its mean is right here. And the experimental group, mean is right here. We saw that when you do a t-test, you get t with degrees of freedom 38 equals 2.22, and the probability of getting a t-value that high or higher is 0.033. Let's look at the regression output and see if we see any similarities. So the intercept, that's when x equals 0. So the line is down here. It's at the mean of the control group. It's the intercept equals 138.95. And it's statistically significant. T with 38 degrees of freedom equals 14.44. P is less than 0.001. What does that mean? That means that the control group, the sample mean for the control group is probably not 0, which is not terribly interesting. What we really want to know is the difference between the groups greater than or less than 0, basically different from 0, since we always do a two-tailed test by default. So we look at the slope. That's how steep is this line. If the slope is 0, then this line would be flat and there would be no real change going from group 0 to group 1. But we've got the 30.19 with a t-score. T with 38 degrees of freedom equals 2.22. P equals 0.033. Which should be pretty surprising because that's the exact same thing as the t-test. The t-test is T 38 degrees of freedom, 2.22, P equals 0.033. But if you think about it, the t-test is the difference between the groups large enough to where you can reject the hypothesis that it's 0. The slope is the same thing. Is the slope of this line going from one group to the other steep enough to where it's not 0? Is it far enough from 0 to where you can conclude that it's not 0? It's the same thing. Mind blown, right? You can keep adding as many groups as you want. I just had 2 groups by adding one dummy code, and the dummy code said it's going to equal 0 if you're in the baseline group, the control group, and it's going to equal 1 if you're in the experimental group. And you can keep adding more dummy codes to have as many groups as you want. You just need dummy codes equal to the number of groups minus 1, because the baseline group is always all zeros for the dummy codes. So if you have 5 groups, you would need 4 dummy codes, and they'd all be set to 0 if you're in group 1. If you're in group 2, you'd put the first dummy code at 1 and all the other ones at 0, so on and so forth. So basically, you have one dummy code saying whether someone's in group 2 or not. Second one is saying whether someone's in group 3 or not, so on and so forth. That might seem a little confusing, and if you're like me, when you first learned about this, you might have to stare at this chart for a long time and then go bang your head against the wall a little bit and then sleep on it and then come back and look at it again. The gist of this, though, is that you can have multiple groups in a regression equation. You just need to add a number of dummy variables to it, and you'll be able to do all the same analyses you normally do with a regression equation. I keep saying it as if you can do it with a regression equation. Really, I should be saying it's already a regression equation, and here's why. So I'm going to go with another example. We'll have 3 groups instead of 2. That means you'd need to do a ANOVA instead of a t-test. So we have our first groups that are the same sample means as before, 138.95 for group 1. I used to call it the control group. I'm going to call it group 1 now. Group 2, which I used to call the experimental group, is now 169.14. And then I've got this third group that's way higher than all the others at 283.80. So if you did an ANOVA on these sample means, I put the ANOVA table here, you get an F of 84.99. That means that the average between group variance and the average residual variance, that first thing is 85 times larger than that second thing. Like the between group variances are way larger on average than the within group averages, the residuals. If that's a little confusing, review the chapters on ANOVA and the chapters going over total and model and residual variance accounted for. I believe that was chapter 5, if I'm not mistaken. But the gist here is just if you were to do an ANOVA on these, it would say that there's a statistically significant difference overall, which in an ANOVA just means at least one of these pairs of groups is different from one another statistically. It doesn't say which pair or how many pairs overall are different from each other. You'd have to do follow-up tests. Now, if you scooch on over to regression land, you would have two dummy codes in your equation. Well, first you have the intercept as usual, and the intercept is just the average for the baseline group, 138.95, which is statistically significant. It's different from 0. And 138.95 is right here. Our predicted y equals the intercept, 138.95. And since if we're predicting the first group, then we would multiply the dummy codes for group 2 and group 3 by 0 because we don't want those in our predictions. They get multiplied by 0. If you want to make a prediction for group 2, then you have the intercept, and then you'd add group 2. This would get multiplied by 1 by the dummy code for group 2. And the dummy code for group 3 would be set to 0 because we're making a prediction for group 2, not for group 3. So this would drop out of the equation. Since the group 3 coefficient is not in the equation, we just have the group 2 coefficient. We would have the intercept plus the group 2 coefficient. So it would be 138.95 plus 30.19. That's the mean of the second group. That's our best prediction we can make, is just predict the mean. And the group 2 coefficient is statistically significant, just like it was before. And what that means is that as group changes from 1 to 2, see, the math changed a little bit, but basically the slope, if you were to draw a line connecting the mean of group 1 to the mean of group 2, that line would be steep enough. See, if it was 0, it'd be flat, but since it's going upward, it's steep. It's steep enough to where it's statistically significant, meaning it's probably not 0. It's not 0, it's too high to be 0, meaning that the difference between groups, see, the difference between group 1 and group 2 is 30.19, and that difference is statistically significant. So this coefficient being statistically significant gives you the same information you would get out of a t-test comparing group 1 and group 2. Now, if you go over to group 3, you want to know what's the best prediction you can make for group 3. So you take the intercept that always gets added to the equation, and then the dummy code for group 2 is set to 0 because we're making a prediction for group 3. So group 2 drops out of the equation. Group 3 gets multiplied, this coefficient gets multiplied by 1 because we're trying to make a prediction for group 3. So our equation becomes y equals the intercept plus the coefficient for group 3. That becomes 138.95 plus 144.85. When you add those together, that becomes the mean for group 3, which is 283.80. And the coefficient for group 3 is statistically significant. That means if you were to draw a line going from group 1, the mean of group 1 to the mean of group 3, this line would be way steeper than 0. If it was 0, it would be completely flat. But since it's sloping upward, it's greater than 0. So it's you have the statistically significant result, basically giving you a green light to conclude that it's not 0. And group 3 is just the difference between the baseline group, group 1, and group 3. And the fact that it's statistically significant tells you that if you were to do a t-test comparing group 1 versus group 3, this difference of 144.85 between the two groups would be statistically significant. So when you do a regression, when you do this ANOVA as a regression, see, when you do an ANOVA, normally you just get the overall output up here, which tells you, yeah, there's some difference among the group means. I'm not going to tell you which one it is. You have to go do follow-up tests. With a regression, it at least tells you that group 2 is different from group 1 and group 3 is different from group 1. You still have to do an extra step to tell if group 2 and group 3 are different from each other, but you get more information when you use the regression framework. I keep saying it like that's an option. The ANOVA really is the same thing as the regression framework. Like, they're mathematically equivalent. In fact, when you look at the regression output, it'll often give you an overall model output, and it has an F value with degrees of freedom and a P value, and those match the ANOVA. See, F with numerator degrees of freedom of 2, denominator degrees of freedom of 57 equals basically 85. That's the same as up here, degrees of freedom 2 and 57, F of 85. They're the same thing. But if you specifically ask for it in a regression output style, which I don't, sometimes it's not even an option in some programs, you have to ask for ANOVA if you want that, you get more information. Two different ways of looking at the same data. The math, according to the math, it's the same, but according to a human, it looks quite different. All right. Like I said at the beginning, there's an added benefit to using a regression approach compared to being stuck with ANOVAs and regressions that only have one continuous independent variable. And one of those benefits is you can have basically two regression lines in the same model. So right here, I've got M. Night Shyamalan and Quentin Tarantino's tomato meter scores plotted in the same scatter plot. I've got Tarantino's tomato meter scores as the black circles and M. Night Shyamalan's movies as the red circles. And these are both looking like they're going down over the years, but down at they're going down at about the same rate, but M. Night Shyamalan's movies kind of started off worse overall than Quentin Tarantino's movies. And they both go down, but like Quentin Tarantino at least started higher and went down from there. M. Night Shyamalan started lower and went down at about the same rate. That's according to the limited data we have. You can actually use regression to have both of these lines in the same model. And the way you do it is you have an intercept that represents your prediction for the baseline category. So for the baseline category, you'd have M. Night Shyamalan. That's the one that the program I use to calculate all this stuff shows M. Night Shyamalan, I think, based on alphabetical order. So the intercept for this model is basically like, look, this is our line that starts at around 60. When year of release is about 1990, 1991. We start our predictions at 60-ish. Then we add to all of our predictions. So we've got intercept plus the coefficient. I hate calling it a slope because there's you can't have multiple slopes for a line. I guess if you have two lines, they can each have a slope. But you have the intercept. That's M. Night Shyamalan tomato meter scores starting at the first year that the data starts on. And then you add what year times how much you go down on your predictions per year. So our predictions, the regression coefficient for year is -59. So basically, if we're just talking about M. Night Shyamalan, we start at around 60, and then for each year you go up from 60, you subtract 0.59 from your predicted tomato meter scores. So over the years, you just keep chipping away at those predictions. That's where this line comes from. It just keeps going down and down and down and down, little bit by little bit. So that intercept and slope gives you M. Night Shyamalan's predictions for his movies. You also have a coefficient up here. It's called slope. I need to make up my mind which one it is. People call it both, and it drives me crazy. You have a coefficient for Tarantino. And basically, you just end up multiplying this Tarantino coefficient by 0 if we're making a prediction about M. Night Shyamalan, so that this just drops out of the equation. Or you multiply it by 1 if you're making a prediction about Quentin Tarantino's movies. And what that does is if you leave that in the equation, then this red line just gets bumped up by, I think it was 34. Let's go back up. 34. Oh, it's basically 35, 34.96. All the same predictions because we're going down by 0.59 for each increase in year. But you just, if you code that dummy code as 1 and leave that in the equation, everything gets bumped up by 35, but it's still going down at the same rate according to our model. So two lines in the same model. And let's look at the statistical output. The intercept for the baseline category of M. Night Shyamalan movies is 57. And again, that's just our red line right here. That's where it starts at 57-ish, goes downhill from there. That's statistically significant. What does that mean? It just means that M. Night Shyamalan started off making movies that were not at 0. So they could get worse. And then our coefficient for year represents the negative slope for both lines. See, this line is going downward. If the slope was 0, then it would just be flat. The tomato meter scores would not be changing at all as the years go by. So it is negative, but our statistical test says P is not less than 0.05. And that means that despite the fact that our line does appear to be negative, there's not enough data to conclude that it is indeed negative. So we would drop our predictions as years go by, but we couldn't, if we were doing research and our research question was, do directors get worse over time? We wouldn't be able to conclude that because this p-value is not significant. And then you have the Quentin Tarantino regression coefficient. That's the gap between this red line and this black line. So if you're adding that 35 to all your predictions, you add the year. So that tells you where on this line you are, but you also add the 35 to boost up your predictions up here to be on the black line. Is that gap between the red line and the black line far enough away from 0? Like, is this gap larger than 0 so much so that we can reject the null hypothesis? That turns out to be a yes. P less than 0.05. That means that this 35 tomato meter score gap between the two directors is statistically significant. So if we were doing research on do directors get worse over time, we wouldn't be able to conclude that, but we would be able to conclude that Quentin Tarantino is a better director than M. Night Shyamalan if you count tomato meter scores as like a definitive measure of who's better. You can debate that all you want. So that's how you can have two regression lines in the same equation. And hopefully you're starting to see that the possibilities really open up to be able to examine your data in different ways. And you can have different combinations of continuous variables and categorical variables with different levels, as many levels as you want. Another thing that you can add is an interaction. So this is the original regression equation on the right where you got the two lines are parallel. When I add an interaction into the model, it ends up not being statistically significant. So over here on the left with the interaction added, the predictions don't actually look that different. I think the red line is the same. The black line may have changed a little bit. Basically, adding an interaction into the model allows you to say that the directors are getting better or worse over time at different rates. So if there was an interaction in the model, if there was a statistically significant interaction, then Quentin Tarantino could be getting worse over time at one rate, and M. Night Shyamalan will be getting worse over time at a faster rate. That's one potential example of an interaction. But there was no interaction in this data. And the math, as far as like regression equations go and having an interaction, gets a little more complicated. So I don't go over it in this setting. But also, it's not really that important to me that you can interpret all the coefficients and like tell me what they mean necessarily. I mean, I might have something on an exam like this coefficient represents the increase in your predicted scores going from the control group to experimental group. This is equivalent to ... I want you to know that that's equivalent to a t-test. Like I want big picture conceptual stuff to be understood. And that's part of the math stuff is part of that, but I'm not as, just for this course, it's not as important to me to make sure everyone's mastered the math part of everything. So I don't go over the math part of the interaction at all. And just to give you more visuals for what an interaction would look like if it were there, here's this chart right here. As X increases, both of these group, the red group and the blue group, both go up, but they go up at different rates. The red group it has a higher, like it's more elevated starting off, and it increases as X increases, but it's not that steep. Like it's not flat, but it's not super steep. The blue group, on the other hand, it starts lower overall, but its slope is so steep that it actually ends up surpassing the red group's regression line. So you can see there's a clear interaction. It's not that the lines are parallel. Here we've got two data sets. One of them has, it's got a teal group. I don't know if that's actually teal. A teal group and an orangish reddish group. And they're both more or less going down at the same rate. As X1 increases, both groups decrease at about the same rate. There's no interaction. And the other data set over here on the right, the teal group has 0 slope, and the orangish reddish group has a slope. It's not very steep, but it is going up. And you can see that the groups are changing at different rates. So the slopes are different. There's an interaction. So if you were to test this data and add an interaction coefficient to the model, that coefficient might very well be statistically significant, meaning that you can conclude that these variables change in response to the X variable at different rates. Well, that's it for this class. I know that last chapter was a lot to take in, but I think it was important, and I hope you enjoyed the plot twist, and you have a great day.